I'm going to talk about the very special way that you can create a superconductor, and it has several very interesting features. Let's recall what's the conventional superconductivity. So it's got two main features. You have dissipationless currents. Current running without resistance does not dissipate energy in the material that is superconducting. You got Masonry effect, which is the expulsion of magnetic field from the bulk of the superconductor. And that's how you manage to create this very strong magnetic force that allows you to float a magnet above the superconductor. And the mechanism behind this conventional superconductivity is called Cooper pairing. You have two electrons pairing with opposite spins and opposite momentum, so they got a zero center of mass momentum. And they create a bound state that is, decays exponentially. So this is V0 is the interaction potential here. And it decays exponentially with interaction potential. So it's a bound state that is always there with some binding energy that is non-zero, no matter how small you make the interaction energy. You can also have a superfluid formed by electron-hole Cooper pairing. So hole is the absence of electron, quasi-particle with the same mass, opposite charge. You can experimentally realize it with bilayers. You have, with some doping, you can create holes in one layer and electrons in another layer, and they would be Cooper paired via attractive Coulomb interaction. And they can also exhibit a superfluid phase below a certain critical temperature. And so the picture, to understand what it actually means to have an electron-hole pairing, it's basically the same as electron in conduction band pairing with electron in the valence band. This is equivalent to electron in conduction band pairing with the hole in the conduction band. What are the different systems that have been realized already to this point with electron-hole superfluid? We have graphene-graphene over here, ballet-graphene, and we have a variety of different quantum wells bilayers where you can also have this electron-hole superfluid. And I have to stress that they're all what I would call non-hybrid, in the sense that in each layer, both particles are described by the same equation. It's either Dirac equation for graphene or ballet graphene, or a Schrödinger equation for quantum wells. But let's ask a question. What happens if we have two layers which are not equivalent in the sense that they have particles described by different equations? So we're looking at the hybrid model. We have Dirac holes in a topological insulator, which are described by the relativistic Dirac equation. And we have a quantum gallium arsenide quantum well for electrons, which have Bayes Schrödinger equation. And it's important to stress that topological insulator is not, it doesn't have a graphene lattice. It may be something completely different. But on the surface of topological insulator, it behaves like graphene. So it has the electrons, the particles on the two-dimensional surface follow the same equation. And they have this asymmetric Dirac Hamiltonian with the symmetry delta. We have two sublattices A and B. And with a symmetry, where, for example, two atoms are inequivalent or you have some external magnetic field, you would have this asymmetric Hamiltonian with this dispersion and with, as an example, with this eigenvector of this Hamiltonian. We can consider the hybrid Cooper pair, which is kind of the simplest thing to think about when you analyze the superfluidity. So we just write the eigenvalue equation for hybrid Cooper pair. You got your Dirac Hamiltonian here, Schrödinger dispersion, interaction potential. We can Fourier transform to momentum space. And the very important point here is that this term, lambda, it's the Dirac spinor overlap. It has these two exponential terms, which create two possibilities for Cooper pairing with distinct orbital angular momenta. And that's what I'm plotting here. It's the binding energy as a function of lattice asymmetry for sublattice B and sublattice A. So you have two hybrid Cooper pairs with distinct binding energies that can be tuned with lattice asymmetry. To formally analyze superfluidity, we need to apply mean field. We need to use mean field to calculate condensation energy, for example. And within this, we have the sublattice degree of freedom. So the order parameter for the hybrid electron-hole superfluid will have two components, and it has this 3×3 Hamiltonian. Importantly, because we have Dirac hole spectrum, Dirac hole pairing with Schrödinger electron, we have Schrödinger electron conduction band interacting with Dirac valence band, hole valence band. And so what we have here is you can see that this band does not participate in superconducting interaction, and that's why we can truncate it from the Hamiltonians to get an effective 2×2 Hamiltonian, where this ZV is special order parameter in the band basis, what I call that order parameter in the valence band order parameter, and it's a superposition of the order parameter for the pairing of the A sublattice and for the pairing of the B sublattice. And it's a superposition using these components, the parameters of the Dirac spinor. So it depends on momentum and it depends on the phase of the particles. So as I promised, we can calculate the condensation energy. It's basically just to figure out if we get a minimum. You take energy of all the superfluid and subtract the energy of the normal state. And that's what I'm plotting here. Is the condensation energy for both channels. This is the reference line. For delta is equal to 0, they're degenerate because they're just the same. And for non-zero symmetry, you can see that the favored sublattice pairing, its minimum in condensation energy becomes deeper, so it becomes more favored, and the order parameter moves to the right, so the gap increases. And the opposite happens for the different sublattice. The minimum becomes more shallow, and it means that basically you're making it less probable for the pairing to occur at that sublattice. Density plot here demonstrates that we have, at zero symmetry, we have two symmetric minimum that only occur for one of the order parameters being 0. And as we increase the symmetry, one of them moves upwards, the other moves to the left and becomes less pronounced. And this minimum, in contrast, becomes more pronounced. And the plot on the left is to demonstrate that we have the order parameter decaying exponentially. So there is always in condensation energy as well. There's always a superfluid state present for both channels, no matter how large you make the symmetry, so this horizontal axis, which is in agreement with the picture that this exponential decay of the binding energy. So you always get a pairing for both channels. This was at zero temperature. To simplify things, you might ask what happens, how do we analyze this system for non-zero temperature? And any statistical system exhibiting a phase transition at non-zero temperature, we use Ginzburg-Landau model. And it's got this it's a function of two order parameters raised to even powers. And we can also show that the free energy has two minima, but only when the temperature goes below two critical temperatures. So if you look at this, temperature here is larger than the critical temperature for the B sublattice and for the A sublattice, so nothing happens. There is no minimum. Here, the temperature is lower than critical temperature at the B sublattice, and this line separates the region where the free energy is smaller than zero from where it's larger than zero, and the minimum appears here. And finally, when the temperature is smaller than both critical temperatures, we got two minima appearing for both sublattices. The second part of the story, a very important part of the story, is topology. So I'm just going to quickly give a couple of definitions. We have parameters coming from the time-dependent quantum mechanics, a Berry connection, which is like magnetic vector potential, Berry curvature, which is like a magnetic field, and finally Chern number, that is like a magnetic flux. And Chern number defines it can be used to separate the system to determine which topological phase you have. So the system may be in different topological phases, and Chern number can be used to determine which one of them is topological, which one of them is not. And it's very directly related to the idea of edge states. Only to calculate the number of edge states between the conduction band and the valence band is to take the difference between the Chern number for the conduction band and subtract the Chern number from the valence band. And that's what I've done for hybrid electron-hole superfluid. So this band is called truncated. This is the upper Bogoliubov band, and this is the lower Bogoliubov band. If we look here, these are the Chern numbers, so this topological invariant that I just described. Let's look at this transition here. If I take the difference of the Chern numbers, it's only non-zero for the upper and lower Bogoliubov bands. So I got edge states between these two bands. Similarly, if I go along this arrow, the only non-zero Chern numbers are for the truncated and for the upper band. So I got edge states between this and this band. And similarly, I can go in this direction, in which case I would have all Chern number differences being non-zero, and so I got edge states between every band. And basically, how do we make sense of it is for transition from delta B to delta A, you might have a region in a real space where all your particles are Cooper pairing at the B sublattice, but some region they're Cooper pairing at the A sublattice, and at the boundary, between these two regions, you would have edge states trapped. You would have edge states moving along the boundary. And similarly, if you can manufacture a lattice that has a positive asymmetry here and negative asymmetry here, at the boundary between these regions, you would have an edge state propagating. So to conclude, 3 main points. We developed a theoretical model for a hybrid excitonic electron-hole superconductor. Its main feature is 2 superconducting states that have different critical temperatures and different condensation energies, and they can be tuned with lattice asymmetry. And these states are also topologically non-trivial and distinct, and they exhibit edge states at the domain boundaries. As an extension, we can think about the probability of pairing, of Cooper pairing at the A sublattice as opposed to B sublattice as opposed to A sublattice. So how are the stable and metastable states related in terms of probability of superfluid pairing? So the end.
Next one. So you had that plot of energy as a function of an ordered parameter with an energy minimum, right? This one, yeah.
Mm-hmm.
So typically, in units of energy, for example, electron volts or whatever, what energies are we looking at?
Yeah, so here delta S0 is the minimizing order parameter with no zero symmetry. So it's basically the point, it's this point for the order parameter. So basically I'm using dimensionless units and I found the minimizing value of the order parameter for no asymmetry, and it's just a ratio. So that's why it's 1 when there's no asymmetry.
I understand, but for an experimentalist, if I wanted to design an experiment, I wanted to know, well, do you have an idea for a real system? What are the characteristic energies?
For the order parameter?
Or that minimum of energy? Clear minimum.
Yeah.
What's the energy difference between that minimum and your zero? In units of energy.
Yeah. Milli-electron volts, but I haven't made any numerical calculations, so yeah, I don't think I can answer. Yeah, no knowledge.
Something, maybe just last question. So, you don't see here explicitly a density of electron-hole pairs. Is that an important physical quantity in your system, or?
So it's absorbed into the coupling constant, the density of states, right? You're talking about
Density of electron-hole pairs.
density of electron-hole pairs.
Is there a difference fundamentally if I have just one electron-hole pair, or?
Yeah, no, I don't think it's very important because we can get all the information without really thinking about the density at this point. I don't see how it I don't see how it would be relevant for the picture.
For superfluid, if I have one electron-hole pair, what's a superfluid? If I have just one electron-hole pair.
Well, you have many electron-hole Cooper pairs, but it's not. We're not specifying the density, so how dense they are. We're only thinking about, okay, you can have electron-hole Cooper pairing at two different sublattices. They can perform superfluid, but as far as the density, it might be, we might be able to calculate it, but I don't know.